In this video we show how to perform simple regression in ILLMO. We use the same example as used in the book by Andy Field. It's a CSV file with two columns. The first column named adverts contains the advertisement cost that has been made and which is used as the independent variable to predict sales, which is seen as the dependent variable, is the sales per week of a record. So this, as it's a CSV file, so the number of cases is 200, which is the number of lines in the file, and we just read it. So this separation character is semicolon. We just read it as a CSV file. The data is interpreted as continuous, and so there's a small manual describing how to set the different columns. So there's no explicit column designing the number, so we use the line number just as the default condition number. So the dependent variable is the sales, and the independent variable is the adverts. And so the data is interpreted as continuous. So as always, the dependent variable, which is sales, is just loaded into the scaled attributes. The independent variables are actually loaded as stimulus patterns. So this is the values for the adverts. As we've indicated in the when we were reading the CSV file, what was the dependent and independent variable, ILLMO has already made the connection. So it's actually using these independent variable to predict the averages for the dependent variable. If you want to get rid of, you click, now this appears on my second screen. So this is the simplified model. So the pattern is input. You have a gain and an offset that predicts the values for the dependent variable, so they're used for the averages for the probability distributions, which are then mapped to the observed histograms. Now the observed histograms are stepwise functions, as there's only one observation for each case. So ILLMO has already performed the linear regression, so if you want to know whether the regression is actually significant, the easiest way is to look at the log likelihood profile for the gain factor, because if there's no significant linear relationship, then this gain factor should not be significantly different from 0, but in this case it is. Similarly, you can look at the log likelihood profile for the other parameters. One of them is the offset, and the third one is just the standard deviation. So they can each be examined. There's some interesting plots, when, for instance, that standard is, this is the scatter plot showing the model prediction, which is actually the independent variable times the gain plus the offset. So these are the values there, plotted against the dependent variable. So if you have a very high correlation, then you would like to see these points along the line. An alternative way of plotting this kind of information is to plot the model versus the data minus the model, which is also called the residue value. So this is the way to do regression in ILLMO. You can also examine the traditional way of regression. So this is the information you would get from a traditional package doing linear regression. So you would get the ANOVA table expressing and, for instance, giving you the fact that the correlation coefficient is 0.578, and it's in between 0.478 and 0.663, which is a kind of classical information. You also get some confidence intervals for the gains and offset according to the traditional statistics, which is based, as always, on the assumption that the data is continuous with the Gaussian probability distribution with constant variance. Now, the assumption of constant variance is obviously a problem with this data set, because you see that the variance is lower for low values of the predictor, so the adverts, and it decreases actually with the values. Now there's a way to handle these kind of cases. It's called generalized linear modeling, and the way to incorporate generalized linear modeling in ILLMO is to include a nonlinearity on the predictor, but then use it in a very special way, not only to predict the averages, but also to predict the standard deviations. Because the theory of generalized linear models says that there's a nonlinear function that you can incorporate, as shown here, which not only predicts the averages, but the derivative to this curve is actually proportional to the standard deviation. And like for any parameter, you can examine whether there's evidence for this nonlinear function by constructing the log likelihood profile. You see that the confidence interval excludes 1. It also excludes 0. So the function is neither logarithmic nor linear. It's somewhere in between. It's somewhere like a square root.